Alright, so let's see if we've got good markers. Let's recall some things. So our goal is to lay our hands on the yellow subspace over here on the front of the book. And the way we're going to do that is we're going to need to recall a couple of things. So we are going to need to recall a span of a set of vectors. Okay, so what is the span of a set of vectors?
Isn't it the linear combination of all those vectors?
Good. So if I say S is the span of these, then what that means is X in S implies that X is some combination, so scalars times vectors, of the vector, so a linear combination of the vectors in my starting set. Yes? Good with this? Okay. Now, we already know one of the subspaces on there, which is the red one. So, this subspace, what's that one?
That's a column.
Good. That's the range, which is the column space. So why is the range the column space? Let me actually draw this picture up here. So I've got my function A going from side to side. Let's see if we can do any better with this marker. I have to carefully match. Oh, that's a good one. Look at how crisp that is. Okay. So far I've got my function A going that way.
Yep.
I have said to you that in here in the middle there is the zero vector. You guys had a handle on this subspace last time. What's this one?
Null space.
Perfect. This is the null space of A, and what I know is that A takes that entire space and pushes it into the zero vector over here. Okay? Okay? A also takes this entire space over here and pushes it into this, which we labeled the column space of A. If you're with me on that? Okay, so to lay our hands on this one, which is the same size as the column space of A, I'm going to have to think a little bit about what it could be. You guys with me on that? So, first, column space of A is defined as what?
The span of all of A's columns.
Perfect. It's the span of the set of the columns of A. So I'm saying that A has n columns, which I'm going to take a convention and say that A is an m by n matrix. You guys all on board with this? Okay. So why is that the range? So this is the range of A, because what?
Didn't that have to do with something about the codomain? Well,
It's definitely in the
codomain
codomain.
is what you're aiming at.
So over here I've got the domain, right? And in this case that's R
M.
M. And over here, wait, M?
Or N. Yeah.
Okay. So I've got Rn over here. Over here, I've got the codomain, which is Rm. So why is it that the column space is the range?
The range is what you actually get.
Yeah, the range is what I actually get, right? Which is sometimes smaller than the codomain. Like sometimes a lot smaller, right? Like in the case of, what's the matrix that has the smallest range possible? Perfect, the zero matrix, very nice guys. So the zero matrix collapses this entire picture to just the zero vector over there. So the null space over here would be everything, and the column space is just the zero vector over there for the zero matrix. You see that? In general, it's some kind of, not quite that, right? But it probably doesn't cover the entire thing. You guys see this? So why is it that the column space is the same as the range?
It's the image, that's,
What happens when you do a matrix to a vector?
It's another vector.
So say I've got, that's good, Logan, it is another vector. No, that wasn't sarcastic, that sounded super fucking sarcastic, sorry. Wasn't meant to be.
it's like, damn.
So here's your matrix A, right? And you're going to do your matrix A to a vector. How long does that vector have to be?
Has to be by n.
Yeah, good. It has to have n coordinates, right? So I'm going to call them x1, x2, down to xn, right? So I've got my matrix A. I'm multiplying it by a vector x. What do I get? Like, how do you do this multiplication?
So it's a bunch of
You get
dot-
x
dot
sub
products.
1.
Okay, you guys want to look at the row picture, right? Which is a bunch of dot products?
Oh, the column picture would be a
Column
bunch of
picture.
linear combination.
Yeah.
It would be a linear combination.
Oh, shit. You guys see that? Like the column picture tells me that the result of multiplying this matrix by this vector is going to give me a sum of these numbers times the columns, right?
Yeah.
Yeah.
So I'm going to get C1x1 plus C2x2 until I get to CNxn, right?
Yeah.
Yeah.
You guys see that shit?
Yeah.
Yeah.
And what is that thing? Well,
Oh, it's a linear combination.
that's a linear combination of the columns.
Which,
Could I get any linear combination of the columns?
Yes.
Yeah, you just plug in the numbers you want to see.
Yeah.
You guys see that?
Yeah.
So this is an element in the span, and every element in the span is achievable.
Oh,
You guys see that?
so that's why it appears as a rectangle, because it's every combination of C, or it's C's.
Yeah, so the reason that I'm drawing rectangles up here, this is good. So the reason I'm drawing rectangles is that they are subspaces, and subspaces are flat and pass through 0. You guys see that?
Yeah.
So I'm drawing these flat. Like that's the kind of thing I'm trying to get across with this rectangle business, is that it's flat. I'm kind of stuck drawing like two-dimensional-ish subspaces, right? These could be arbitrary dimensional, right? But they are definitely flat and they definitely pass through 0 because they're subspaces. You guys see that? Okay, so now I'm like entirely sure that the column space is the range. And if I had to fill in like a word in this sentence, I'd say this is the range of A because, like, what is this a drawing of? This is like symbols for, like, closed column. Yeah, this is symbols for the column picture. You guys see that?
Oh.
Like, it's inevitable. I'm not presenting a proof here because this is inevitable. Like, this is what the definition says it is. You guys see that? If we were presenting a proof, we would be concerned that we need to show double containment, right? So we need to show that anything in the range is in the span of the columns, and that anything in the span of the columns is in the range. But I think that's pretty clear here. You guys see that? I can achieve any linear combination by picking the coefficients exactly the same, and any combination can be achieved. You see see that? And any range element I can get as a linear combination, same reason, right? Write down the combination. It's good with this? Okay, so this goes that way, right? Now, I want to lay my hands on this thing. There's a couple different thoughts we could have here. The first one is, how long are the vectors here? Good, they're n, right? They're members of Rn.
Yeah.
Okay. What up here on the board has n things in it? Like, what are my n vectors kicking around? Because my columns, where are those? Yeah, they're m long, which I know because they're over here. You guys see that? Like, if I want to hit one of the columns, I just one-hot a domain vector, right? Okay, so I know the columns are over here in the codomain. So what is it about my matrix that might be over here in the domain?
The rows?
Yeah, the rows.
Yeah.
You guys see that? So maybe, just maybe, this thing could be the rows. You guys see that? Okay, now I'm going to write that up here, but I'm going to write that up here using, what the hell? I'll write it up here as row, okay, so now I really should figure out that the row space and the null space don't overlap at all. You guys see that? Oh shit, how do I figure that out? Okay, let's do an actual little proof thing here. I'm going to claim something wild. You guys ready for this? I'm going to claim that the only thing in common between the null space and the row space is this zero vector.
The row space and the null space?
Yeah.
Okay.
Is that what I said?
Yeah.
So my claim is, if I take the row space of A, which I really haven't quite defined yet, and intersect that with the null space of A, I only get the zero. Is with me on that? Okay, so first I probably should define the row space of A since I didn't do that. What's your definition for the row space?
All linear combinations of the rows of it?
Good. Should be the span of the rows. You guys see that? So let's throw that definition just down here in the corner quick. I'm not super concerned with like making a really formal statement here because you guys, like, this is pretty straightforward. It's the same thing as the column space, right?
Yeah.
So row of A is defined to be the span of the set of rows. How many rows are there? M. Good, good? Okay. Now, just need, God, that's weird, right? Feels like, why can't a row, God, why can't a row go to 0?
Well,
I'm going to just suppose that this isn't true. You guys see that? So, well, I'm going to kind of heuristically suppose that it's not true. I'm going to say, let there be an x, right? So suppose that I've got an x that's in the row space of A, and x is also in the null space of A. You guys with me on that? Have I lost you guys with symbols here? Okay, so suppose I've got an x in both places. If x is in the row space, what does that mean?
It has to be a linear combination of the rows.
Perfect. It's some linear combination of the rows, right? So x is A1 R1 plus A2 R2 plus up to some AM RM. Right? Right, it's in the row space, so there's some set of coefficients that I could multiply by all the rows to get this thing. Okay, see that? That's what it means to be in the span of the rows. Okay, now that I've got something that I know is in the span of the rows, it's also in the null space, right?
Yes.
You guys see that? So, I guess I'm going to take A and do it to this. You guys see that?
Yeah.
And I'm going to know that I get 0. You guys see that? So I'm just going to say, consider AX. And I'm going to do A to X. This should be 0 because X is in the null space. You guys all with me on that? Okay, I'm going to dump some stuff over here. Okay, so we're doing A to X. That means I'm doing A to a linear combination of stuff, right? So I'm going, alright, so A done to X is A done to A1 R1 plus AM RM. You guys all with me on that? And I know the sizes make sense. Why do I know the sizes make sense?
Because the rows have a size graph.
Yeah, because the rows are the right size. We established that a bit ago. So, I'm going to do this, right? And I'm going to say, alright, so that's going to be A1, A done to R1, right? You guys see that? And then I'm going to get A2, and that's going to be A done to R2. I put parentheses there because I was really thinking function hard. You guys with me on that?
Yeah.
Okay, so we're going to get AM. That's going to be done to the nth row. Okay.
Oh,
See it?
yeah.
Where is it?
If you do a row onto that vector, it's going to be doing it onto itself. And if it's doing it onto itself, then that means it would have to be into the 0 vector to achieve 0, otherwise it would achieve a number greater than 0. Or a dot product of itself, so that makes sense.
It's like going from like 3D to 2D and 3D.
Okay, so hold on. I think I'm with you. Let's write that down really carefully. So I'm doing A to row 1, right? You guys with me on that? So that's me saying, all right, let me just, I need a margin, no, margin, over here. I just want to do A to Ri quick, right? Oh, what the hell, let's just do it to R1. So A looks like rows, right? So it's row 1, and then it's more rows, right? Rows equal. How many rows is it? M rows, perfect. And I'm doing this to R1, and so if I do the row multiplication picture, right? You guys see that? That's going to give me R1 dotted with R1, R1 dotted with R2, and kind of so forth, right? And I don't really know what R1 dotted with R2 or R1 dotted with any of the rest of these is. You guys see that? But I do know that R1 dotted with R1 is going to be the magnitude of row 1 squared. You guys see that? And then I kind of don't know what's in the rest of these. You guys see this? Okay. How does that help?
Well, the magnitude of R1 will always be greater than 0 unless R1 is equal to 0.
Okay. That seems like a good thing.
Well, it's not good if we're saying that it's equal to 0, because then we're saying that basically 1 is equal to 0.
Well, keep in mind I've got other stuff to add, right? You guys see that? No. And I'm concerned that maybe the other stuff adds up to 0. You guys see that? Let's see. Okay. Huh. That might be problematic. Because the other stuff could certainly be negative, right? So this is A done to R1. You might have to pull on this a different way. You guys see that? Uh-oh. Let's see. So my concern, right? Huh. You guys see it?
Concern. I want to hear your concern. I have many concerns right now, but I want to hear your concern.
Okay, so my concern is I've got all these A's, right?
Yeah.
And I know that AX should be the 0 vector, right?
Yep.
You guys see that? So I've got A1 and like, okay, so I've got this whole like mishmash of frickin' rows, right? So I've got A1 and this is multiplied by like, yeah, well, like there's a whole bunch of stuff. I know that I've got something positive up here in the top unless the row is 0. You guys that?
Yeah.
And then I'm like, okay, well, I'm going to add these all up and I'm going to get 0. Well, frick, man. I just don't know what's in the others. You guys see that?
Yeah.
Okay, so this next one is R1 dotted with R2, right? You guys see that? And the next one is R1 dotted with R3, so on until we get to R1 dotted with RM, right? And I kind of thought we had this. And we were like, oh, well, that's positive, and if I take this thing times a positive thing, and I'm supposed to get 0 in that component. The problem is that there's all these other ones, right? And they're multiplied by A's. So I'm kind of like, oh, well, maybe they all like freaking cancel out or something.
So you go down like diagonally, it's always going to be like that one positive.
Yeah, there'll always be a positive one, right? But they're all kind of like down the freaking diagonal or some weird thing.
Yeah.
So I'm like, maybe they all like cancel out somehow. Let me write down the next one. Like maybe we can sort this out still. You guys have this happen when you're trying to prove stuff? You get like partway through and then you get lost? Like shit happens, for sure. I'm not sure I'm not lost right now. I know another way to show this. I decided to venture down this path because I thought it might be fun for you guys to see a little bit of lostness. Like this happens. Don't be worried about it. I really worry when I present like super clean arguments up here that I've already thought out, that you guys don't get a feel for being lost occasionally. I'm not sure this is going to go this way. Is cool with that? So let's adventure together a little bit. Like, fucking, what's the next one?
Row 1, whatever, then row 2 would be magnitude of row 2 squared.
Okay, so I know that the second one's going to be the magnitude of row 2 squared. That's for sure.
Yeah.
What's the top one?
R1 dotted, or R1 dot R2. Yeah, I noticed that.
Okay, that's giving me a little hope that we might be able to get this thing back on the friggin' rails. You guys see that? Okay, so let's get them all here, right?
Yep.
So I've got A3, that first thing's going to be R1 dotted with R3, the second one's going to be R2 dotted with R3, the third one's going to be R3 dotted with R3, and kind of so forth, right? Is all with me? Okay. And we're going to have some dots, and then we'll have plus, and we'll have an AM, and here we'll have a very similar thing, right? We'll have row 1 dotted with row 2, row 2, or row 2 dot, oh, what did I say, row 2?
Row M.
Row M. This one will be row 2 dotted with row M, this one will be row 3 dotted with row M, until we get to RM dotted with RM. You guys see that? Okay. So what that means is that, like, if I pull the first equation out of that whole thing, right? First equation out of the row picture, 0 is A1, R1 dotted with R1, plus A2, R1 dotted with R2, and all the way out to AM, R1 dotted with RM. You guys see that? Okay. And 0 is also
All the rest of the stuff in the other rows.
that's the same. Let's see, so this equation is going to be row 1 dotted with row 2. So this one's the same thing except we're dotting with row, oh, what did I, you guys let me get away with it. These are row 1
Yeah.
for dotting.
Yeah.
My next one's going to be A1, and we're going to have now row 2 dotted with everything. I screwed myself up a little bit in that I wrote this one backwards from the rest. You guys see that? That's why this looks funny.
No.
Right, because then this one is, I'm dotting with row 2, this one's dotting with row 3, this one's dotting with row M.
Yep.
So this is going to be the same thing except I'm doing, oh no, this one's backwards. Perfect, good work, Joe. So this is going to be row 2 dotted with all of these guys. So A2, row 2 dotted with row 2.
It's all the same.
You guys see that?
Yeah.
Oh.
Like, except for the scalar applied to each one, they're
Yeah.
all like the same term. They just moved around.
Cross.
Well,
It's kind of weird, right? Like, zeros, any one of the rows multiplied through. You guys see that? Like, when I dot product every row with any one of the rows and multiply through by these same coefficients, I always get 0. That's weird, right?
yeah.
That kind of makes me want to do something like, I don't know, like, set 2 of these equal to each other or something. You guys think that's cool?
Oh God, please no.
Is it a path I want to go down?
No.
No, I mean, I'm
Shit,
down.
man, I'm not sure.
Well,
I mean, it's not insight, but at what cost?
You could remove-
Yeah, I think this might provide some insight, but at a pretty deep cost of writing down a bunch of algebra up here. You guys see that? Do you ever get into that feeling? So, usually in linear algebra, this happens when you've picked the wrong picture to look at. So, if we go back to the beginning here, I suppose that x was in the row space, right? That was kind of my starting point. I wrote x out as though it was in the row space. And then I said, okay, so let's consider ax, because it's also in the null space. And now I'm trying to like push this thing around. You guys see that? Okay. That feels really inconvenient. And we've spent like 20 minutes, right? So the kind of proof thing that I want you to get today is the flavor of like, okay, look, this got a little deep. I'm not going to throw this away yet, because I might be able to salvage it if I can't do the other thing. But I had x in two places, right? You see that?
Yes.
I'm going to try switching that thought. You see that? So I'm just going to flip this thought over and try the other thing quick and see if it goes easier. You guys with me? So I started thinking that x was in the row space. So let's just throw that quick alternative thought up and see if we can get it done that way. Maybe it'll give us some insight even if we can't get it done. You guys with me? Okay, so instead of saying x is in the row space, let me start the other way. Let me start and say, okay, rethink. What if x is in the null space? What does that mean? Okay, that means a done to x is the 0 vector. Okay, I'm thinking about rows, right?
Yeah.
Okay, so there's like rows that build A.
Yeah.
And there are m of them. And I'm doing this to some vector x, right? And I'm supposed to get the 0 vector out of this.
Yeah.
Okay? So how do I do x to rows? Like, how do I do rows to x? Sorry, I said that backwards. Yeah, dots, right? So we apply the row multiplication picture and we say, okay, so the result of this, right, this being ax, right, is, what's a vector? And it's row 1 dotted with x, and it's row 2 dotted with x, and it's row m dotted with x, and that's supposed to be the 0 vector, right?
Yeah.
Right.
That works.
You guys see it?
Yeah.
See the thing? What's the thing? What am I supposed to see?
So the dot product of vector x with every row is equal to 0.
What does it mean when the dot product is 0?
Perpendicular.
Yeah, it means it's freaking perpendicular. So R1 is perpendicular to x,
And R2 is perpendicular. Everything is
and
perpendicular.
R2 is perpendicular to x, and Rm is perpendicular to x. Oops, that's.
And we're told that subspaces are flat, so we shouldn't.
You guys see that? It's got to be perpendicular.
And the rows are perpendicular to itself.
Yeah, the rows aren't perpendicular to themselves. That's this thing. Unless they're the 0 row. You guys see that? So, if x is perpendicular to all the rows, you see that?
Yes.
Then it has to be the 0 vector if it's also in the row space. You guys see why? Yeah, in order for it to be perpendicular to all the, so if it was in the row space, right? Then it would look like this. And things like this are only perpendicular to all the rows if all the coefficients are 0. You see how weird that was? The moral of this is like, okay, so I actually got something for free out of this. You guys see that? I erased my big picture. What's the thing I got for free? So I'm talking about the domain side, right?
Yeah.
So I got the row space of A and null space of A. We just showed that the intersection between the two is only the 0 vector. But we got a bonus. What's the bonus we got?
Oh, wouldn't it be the same for the other side?
I don't even know what the subspaces are. Like on the other side,
So,
so over here, I've got,
column space. Yes.
I know this is the column space. I don't have a name for this one yet. You guys see that? Okay, so I'm a little screwed on that one so far. We'll figure, I'll tell you later, probably in 10 minutes. But I got something else for free here. You guys see what I got? I got that a vector in the null space is perpendicular to all the rows. You guys see that?
Yes.
And I used that to say, right, like after this, I used that to say that x has to be the 0 vector if x is in the row space as well. You guys see that? Like that was the punchline of this?
Yeah.
But that seems more important. The thing I got for free is that the null space is perpendicular to the rows. You see that? So I'm going to put a right in here. And you'll notice there's one on the front of the book. They didn't put it in, but it's there. Right? So this is actually clutch. This space is perpendicular to that one. You guys see that? So if I have a matrix that say has a null space, like let's let B be the matrix full of ones, right? Anybody eyeball the null space of this? So it's the span of something, right? Somebody find me a non-zero vector that goes to 0, lickety-split here.
-1, 1.
Good. Okay, how'd you do that?
I did a quick dot product and realized it was 0, and then I just knew I was going to do it for the rest.
Uh-huh. You looked at the rows and you said what's perpendicular to the rows. You guys see that? So, in two-dimensional space, right? The domain of this function b, right? There's a row space. That's the span of the vector 1, 1. So 1 over 1 up looks like this. This is the row space of b, right there.
Okay.
Where's the null space?
Negative. Oh yeah, it is perpendicular.
It's the perpendicular of that.
That's kind of crazy.
That was supposed to be, what symbol is that? That was supposed to be a b. And they intersect at a right angle. And they go through 0. Because they have to. There's no other way for this to work. You guys see that? So I got something for free, and it's super cool. It's that I can grab that null space out of the rows. So if you look at the row space, and in this case it's relatively easy to look at that row space and be like, oh, it's the span of the vector 1, 1. Oh, what's perpendicular to 1, 1? Negative 1, 1 is. Well, there's your null space. No augments necessary.
Sick.
You guys see that? So in 3D, right, you can have the entire place be the row space, and then 0 is perpendicular to it. That's your null space. Or you can have a two-dimensional plane and a line sticking straight out of it. Right, row space is two-dimensional, null space is 1. Or you can have it the other way, right, where the null space is two-dimensional and the row space is one-dimensional. What's the other option?
Where it's two planes. Wait, no.
Yeah, so
The first, can you see the first options again?
yeah, so the first option is something like the identity matrix.
Right.
Right, so we're talking R3. Right, so I'm just going to do R3 back to itself options. So, right, so 3 by 3 matrices.
Right.
Is both me?
Yes.
So option kind of 1 is things like the identity matrix. Right? They have an inverse specifically, right? And so the null space is the 0 vector, right? And the row space is all of R3. And then we could have things where we have two linearly independent rows. So that would be things like, getting really, really lazy on this one. Things like the identity except with a row of zeros. You guys with me? Things that were ref to two pivots, right?
Yeah.
Okay, so this guy's got a null space that's a line. Right, there's a one-dimensional null space. In this case specifically, what is that null space?
All of our one.
Look at the rows. So the rows are
Oh, that's the
I and J,
So
and
it's,
so the null space has to be,
it's XY, right?
so the row space is two-dimensional. It's the span of I and J.
Yeah.
So the null space would be the span of 0, 0, and the C.
Good. The null space is the span of K.
Ah.
Right, the vector
Oh.
0, 0, 1.
That's sick.
You guys see that?
Interesting.
So that's a plane is your row space, and it has a stick stuck through it that's your null. Right, so that's, in this case, the xy plane and the z axis. What's that? Yeah,
Yeah, it is.
and it's a normal vector. How do I know it's a normal vector?
What?
Because it's perpendicular!
Yeah. Break
Right, isn't that cool? It just comes, it all comes together right here. It's super neat.
Yeah.
So this is one of those moments in linear algebra where you're like, wait, what the fuck? Like, I tried to calculate this one way and it was really hard and didn't really show me anything, and then I tried to calculate it the other way, and out of the other ways, I just got something for free that's amazing. Right? So I've got a null that's a line and a row that's a plane. So what's option 3?
Where it's a point in the plane?
Yeah, so the null's going to be a plane, and the row's going to be,
Zero.
so if the null's a plane,
The row's a long.
the row's a line.
Yeah.
I'm kind of using something here that's maybe not totally in evidence, that those two things exhaust the space. You guys see that? We're going to get dimensions, I promise, later today. And then we'll rephrase the counting theorem and this will all come out in the wash. So, how would I make a matrix like this? What's an example?
1, and then the rest just zeros.
Perfect. So in this case, the null space is which plane?
JK.
Yeah, that's the span of J and K, so the YZ plane.
Yeah.
And then the or the row space is the span of I, so the x-axis. I'm flipping back and forth between some kind of Calc 3 or physics notation in this. Are you guys okay with that? That all making sense? Okay. And then what's option 4?
Where
Yeah,
the
bro,
row-
it's 3 dimensions, so obviously there's 4 options.
where
Like,
the-
come
the-
on.
The row space is 0, and then the null space is all of R3?
Perfect. Switch
Let's
these.
go.
That one's actually easier to write down. You guys see that?
Yep,
So how do I get the null space to be all of R3?
you say it's 0.
Okay. So the only matrix like that's going to be the 0 matrix. You guys see that? So there is a 4th option, but there's only one kind of
One
cartoon
case.
there, right? So that'd be the null space is everything, and the row space is just the 0 vector. You guys see that? Cool, cool. Alright. Long enough, that video's super long.
You have to cut it up into 4 points.